So I'm going to tell you about Lagrange multipliers, which you may think as a different point of view for solving optimization problems. By the way, before I begin, just in case you're not able to read the labels, this is a graviton, this is a tachyon, and if you're interested, you should Google them to see what they're supposed to be in particle physics. But let me explain to you how Lagrange multipliers are supposed to work by going back to an example that we had discussed in the past. So this was the problem about the volume and the boxes. So we were trying to make certain boxes As you may remember, this was the last thing we discussed in class. And the point of these boxes is that no matter how you build them, they must have the same volume. So the idea, if you call the size x, y, and z, is that x times y times z was b, right, which was the volume of the box, and this was supposed to be a fixed quantity. Right, so in practice, you could think of B as a gallon, 2 gallons, 2 liters, or whatever particular unit of volume you like. And so, again, like we had to make boxes under this condition that their volume had to be this known quantity. And depending on which particular design you choose, then the surface area of the boxes are going to be different. So remember that the formula for the surface area of a box was this one. And the issue we had with this formula is that this formula depends on 3 variables, x, y, and z, and the only criteria that I gave you for finding critical points and classifying them required you to have 2 different variables, right? So what we did in class is that you could use the first equation, right, to solve for one of the variables. So you could say that z equals v over xy, right? And then you would replace that into the second equation to get like the function of x and y, and you would get you should not. The first one is unaffected because that does not involve c, but in the other 2 factors you would replace c, and so you get okay. And now once you have this function of 2 variables, right, we would set the partial derivatives equal to 0, and we would then classify the critical points that we got using the second derivative test in terms of the Hessian and the determinant of the Hessian, etc. If you remember, basically the answer at the end of the day was that each of the sides of the box, right, if you wanted to remember that the goal was to minimize this quantity. So presumably because the least amount of area would require the minimum amount of money spent on building the box. And what we found is that this the values that would minimize this surface area was simply making the box as a cube, right? So that means that each side must be of the same length and equal to the cubic root of the volume, which again was fixed from the beginning. And so the point of view that we took here is that we didn't want to work with three variables, so we used the first equation to get rid of one of the variables, right? And then substitute it into the expression for A in order to get a function of two variables. But as you may observe, the issue with this approach is that really in this formula, all the variables, for both formulas actually, all the variables are sort of indistinguishable. There's no reason why you should sacrifice C and write it as a function of x and y, and not, for example, write x as a function of y and z. So really, what we would like is a method that's more symmetric and does not distinguish a lot between the does not prefer any variable over the other. And that's the idea of like the Lagrange multiplier method. It would allow you to deal with optimization problems in a way that's more symmetric. And it will have other practical purposes, as we will see later once I make some other examples. But so, what's the point of view for the Lagrange multipliers? So let me think about this in a slightly different way, which is the following. Let's think of this function this function A, and call it f, and you'll see why in a moment. That's just like the standard notation. Okay, so now you have this function of three variables. For practical purposes, it's like convenient again to think of this function f as a scalar field. So maybe this is the temperature at the point x, y, z. So at the point x, y, z, you measure this number. Okay. And now this is what we're trying to minimize, right? This quantity. And the point is that we want to minimize this, but using some extra information. And the extra information is that x, y, and z, when multiplied, needs to give you need them to give you this fixed value of b. Okay. So there's this extra condition, which is called a constraint equation. Which is that, let me call it like this, g of x, y, z equals x, y, z minus b equals 0. Okay, and why am I writing this same equation in this way? Well, because let's think about this equation for a second. If I had given you a slightly different equation, right, like x squared plus y squared plus c squared equals r squared, right? What I'm doing here is, if you want to compare this equation to what I'm doing here, I would move the r squared to the other side. And regardless of how I write it, you should think of this as the equation of a sphere centered at the origin. Right, so here you have a sphere of radius r, and the points that satisfy this equation really represents this sphere. Okay, so in general, the ideas we had discussed in the past is that whenever you see an equation like this, you should think of this as the equation of a surface. Okay, so this is so really, the point of view that we want to take is that here you have some surface. So in 3D space, you have this surface, this membrane, which represents all the points where x, y, z equals v. Okay? And so one way to think about these two equations at the same time is that this function is what you want to measure. So this is like the temperature, right? The temperature at any point in space, x, y, z. But actually, you're sort of being forced to live on the surface being defined by this equation. So really, what you should think is that you only care about the values of the temperature when measured on the surface. Okay, so you're measuring F on this surface. So again, maybe you have a point xyz on this surface, and on this point you get some value for the temperature, which we're calling f of x, y, z. You could have measured the temperature at this point, but you don't really care about this point because that's outside the surface. So it's sort of like, if you think of the surface as a planet, right? You're just allowed to make measurements on the surface of the on your planet and not outside of it. Okay, and this changes a little bit what you mean by an optimization problem, because now again we were trying to find the values of x, y, z, which make this as small as possible, right? But remember that a local minimum is something like a relative notion. So a local minimum means that you're the smallest value that your field takes with respect to other points which are sufficiently close. So it doesn't really matter if the temperature reaches its lowest value somewhere outside the surface, because you're not trying to make measurements at that point, right? So you're only trying to compare temperature values between different points on the surface, okay? So the minima that we want to find are just minima with respect to points on the surface, not like with respect to all possible points where you can measure this function. Okay. So just to compare what the different approaches are, imagine that we didn't have this condition, right? So you just have this function f. So easy case. Well, in that case, again, when you are given a function, the way in which you would find the critical points, right, would be by setting the partial derivatives equal to 0. right? But saying that all partial derivatives must equal 0 is the same as saying that the gradient has to be 0 at that point, right? If you think of the gradient of f as a vector of partial derivatives, so when you only have this function to worry about, the way in which you would have found the critical points was by solving these three separate equations, right? Each partial derivative being equal to 0. Now, a useful way to think about this, and let me go here because I still don't want to erase any of what I'm doing so far. So, what do you know if the gradient is 0? So let's think about that for a moment. So again, we're no longer concerned about the surface for this moment because we are ignoring it. So we just have this function at any point x, y, z. Right, so maybe you can measure the temperature at this point, maybe you can measure the temperature at this point. Okay? And let's say that this is one of the special critical points. So this is a point where the gradient vanishes, right? And so the consequence of the gradient vanishing is that, say, imagine that you are at this point at this critical point, and you're starting to move in a direction v. Okay? Along this vector v, you could measure the rate of change in temperature. Remember, that's the directional derivative, right? And the directional derivative in direction v, right? Well, the formula is that this should be the dot product between the direction vector and the gradient right? And let me wait for a couple of seconds so that you think about this, but what should the directional derivative be at this particular point if you are situated at a critical point, right? What do you think that should be? Well, because this is a critical point, right? I just said that the gradient had to be 0. Right, at critical points. And so that means that the directional derivative in any possible direction is always 0. Right, so this is important enough that we should write it separately. So what I'm trying to say, just to summarize this discussion, is that if you have a critical point of f, then then all directional derivatives vanish. So you could think of critical points as having this particular property of being those points where all directional derivatives are zero. And so why is that a useful perspective to have? Okay, let's try to go back to this situation, which is the one we are actually interested in. So now, again, we have the same function. This is a temperature function, right? This is the temperature you measure at the point x, y, z. We want to know how big or small this function can get, or this field can become, but only when you're making measurements along a certain surface, right? So now you are no longer interested in the temperature along the entire universe. You only care about the temperature on this surface that I drew before. Okay? So the idea is that with respect to this surface, there should be a slightly different notion of a critical point. So what's a critical point? So now let's do this case where the surface is present. So we want to say now that a point P, okay, you should think of this as some sort of definition. So P is now a critical point so again, I'm saying this will be a critical point of this field, right, or any other formula that I write to you. But now relative is more like of a relative notion, not like an absolute notion. So you're going to say that this is a critical point relative to a surface. And again, remember that all the equations of the surface, I want to think of them as being an equation of the form g of x, y, z equals 0. Okay? So an expression like this. So what's going to happen now? Again, in the case where the surface was not present, being a critical point was the same as having all the directional derivatives being 0. So now what we're going to say is that you're going to be a critical point relative with respect to a surface if all the directional derivatives vanish. So we want all the directional derivatives to be 0, but now the only vectors that we care about are not all possible vectors in space, but rather only the vectors which are tangent to the surface. So to explain this a little bit differently, I think you may remember the umbrella. So again, think of the surface. Think of this umbrella as being the equation defined by a surface. So you're trying to, let me draw a point on the surface. So I'm saying, imagine you have this point on the surface P, which I'm calling P here, and I'm claiming that this should be like a critical point for the temperature. So at each point on the surface, at each point on this umbrella, you're measuring the temperature, and I want to call this a critical point, okay? And so my definition of critical point, again, is the following. There are multiple directions. When you're on this point, right, there are multiple directions that you can use to move around the surface, right? So you're here, you can move it in all these tangent directions, okay? But there are also some, well, so the first thing that I'm saying is that for any such tangent direction that you are choosing, the directional derivative should vanish. So for example, this is a tangent direction, and in this direction, if you're really a critical point, your directional derivative should be 0. On the other hand, there are other directions you could use. For example, you could use this direction, right? I don't know if it's too easy to see, but the point is that if you use this direction, if you start at this dot and move in this direction, it's almost like a rocket. It will take you away from the surface, right? And the rules of the game is that you cannot exit your planet. So there are directions that you no longer need to worry about. That's the whole point of what I'm saying. And so, from a slightly different perspective, what I'm trying to say is that, again, if this is the pink point that we drew on the surface, remember that on the surface there's always a tangent plane, okay? And I'm saying that you only need to worry about those directions which belong to the tangent plane. So remember that on any plane, there are sort of like different directions in which you can move. And I'm just saying you have to worry about those directions. You don't need to worry about directions which do not lie on this tangent plane. Okay? So what are the consequences of this? Well, let's go back here. I think this is the best place to erase something. So what I'm saying is that we want this directional derivative to be 0. We have a formula for the directional derivative all the time. Again, remember that the directional derivative is always the dot product between the gradient and the velocity vector. Okay? So what that means is that the gradient should be perpendicular to all the velocity vectors. So this gradient is orthogonal to all the velocity vectors on the tangent plane. But so that means that it has to make a 90-degree angle with respect to any of these blue vectors, but we already know a vector, so I'm drawing it here. I'll do the picture again just for clarity. So again, I'm saying you have this surface, we have this point which is going to be a critical point for the surface, we have this tangent plane at that critical point, we have velocity vectors at this critical point, right, which belong to the tangent plane. And I'm saying that the gradient of the function f, at this critical point, the main property that's occurring, or the main feature, is that at this point the gradient of the function f that we were trying to minimize or maximize happens to be perpendicular to all the velocity vectors. Okay? So in other words, and this is the key point, this is a normal vector for the tangent plane. Remember that to specify a plane, you need to know a vector perpendicular to it. So what that means at a critical point, the gradient is the normal vector. But now, if you remember, this surface arose from some equation, right? The equation that we had before was x, y, z equals v. So this is really the equation g of x, y, z equals v, or equals 0. And so there's another way that we had for finding the normal vector if you started from this equation, if you remember, which was with the gradient of the surface, right, of the equation defining the surface. So remember that in general, not just when you are at a critical point, the way for finding the equation of the tangent plane was to compute the gradient of the surface, and then that would be your normal vector. So that means that you have two vectors which are perpendicular to the tangent plane, and since we are in dimension 3, there's not a lot of room, and therefore these two vectors must be parallel. Okay? So that's a key idea of the Lagrange multiplier method. So the key idea is that at a critical point, both the gradient of the function you're minimizing and the gradient of the surface are parallel. Okay? And so since they're parallel, that means that one is a multiple of the other. And so we will write this as so that means that the gradient, the gradient of f has to be the gradient of g times some number lambda. Okay, let me write it here again in case you cannot see it very clearly. So again, the gradient of f has to be lambda times the gradient of g. This lambda is some constant called the Lagrange multiplier. Okay, so what I will do in the next video is just summarize this, tell you what the Lagrange multiplier method, how it's supposed to work, and apply it to this example of the box so that you see what the main difference is, the main difference in perspective with respect to what we had done before is. Okay?